In this tutorial, we will be looking at Solidworks Plastics. Now, Solidworks Plastics is a simulation-based add-in that predicts how melted plastic will flow through an injection mold, as well as how to avoid manufacturing defects during the packing and cooling process. So the way to add this add-in to Solidworks is to come over to your tabs, right-click, and select Solidworks Plastics from the drop-down menu. When it comes up, you can click on it and you can see a bunch of new buttons here. If you don't find it within your drop-down menu, you may need to come up to your Options tab, click on the little arrow, and then select Add-ins here, and you'll be able to select it from there. So we can go to the Get Started wizard to begin. And if I come over to this tab, you can see that this is what's loaded when you first start a simulation. And the first thing to understand about simulation is that the geometry of your part will not be used in the study. The reason is because using the exact geometry of your part would tax your computer too much and likely crash it. So instead, we create what is called a mesh. The mesh is a geometric representation of the part made of hexahedral elements. So if you were thrown off by the word hexahedral, just remember that the software is breaking your part up into blocks it can understand to use as the geometry for the simulation. So if we choose solid up here under the mesh tab, it breaks the part into 3D blocks. Now if we click shell and use shell instead, it's going to break only the surfaces of the part into 2D shapes. Now this is less accurate because your part is essentially empty. Why would we use shell over solid, you may ask? Because it taxes your computer system a lot less. You would only be using the outer surfaces for your simulation and not the entire part. And so the less computing power that we need, the faster the processing time is going to be, and the less chance that the whole computer system will crash and all those sorts of things. So I'm going to come over here, and under the Mesh tab, I'm going to select Solid. So I need to come out and exit the wizard mode. We're going to get out of that for now. And I'm going to right-click on Solid, and I'm going to click on Manual. And so the first thing you're going to see here is it's asking me if I want to select runner and cooling system design or a virtual mold generation. Now, you would select runner and cooling system design if you actually modeled your runner and cooling system, meaning that you have your gate set up, you have your runner set up, and you have your sprue and any other sort of shutoffs or anything else that you've designed to be part of your part. Virtual mold generation is exactly what it sounds like. If you have a mold that you created and you want to use that as part of your simulation, you would select this. But because of the fact that we're only doing a simulation on this single part, we're not going to select any of these options. So I'm going to come to the next window and I'm going to hit no. I've used previous meshing parameters on this part, but we want to start from scratch here. So there's only one cavity, that's this part, and that's the only thing that we can select here. So we're going to continue. And the next thing you're going to see here is it's asking about triangle size. Remember how I was talking about the tetrahedrons before? This is exactly where it comes into play. The triangle size is the size of the shapes that are going to create the mesh, which are going to be a representation of your part. So let's try to visualize that a little bit more by coming down here and just clicking Mesh, the way that everything is set up by default. Now when I do that, you can see that my part has now been basically transformed into a bunch of these shapes. Now, there are definitely a lot of issues that you may notice between my regular part geometry and the geometry of the mesh that SolidWorks has created. You may have noticed before that I had fillets here. Now, because of the triangle size that we have selected, none of those fillets are visible because these triangles are so large that they could not fit inside of that little fillet. There was also a fillet here, but you could see that SolidWorks kind of abbreviated that fillet by filling it in with these closed shapes. So this is not good enough for us. This doesn't help us that much. So as I mentioned before, the biggest problem here is that the triangles are way too large. I can come over here to triangle size and set this to be, right now it's 1.9. Let's set it to 3 and click mesh now. So you can see that the triangles are larger. That's not what we want. You can see that it actually has an even worse representation than before. So before we had about 1.9, so let's say set this to 0.3 and hit mesh. You're going to see it takes a little bit longer this time. The reason is because the more triangles you have, the longer it takes to process and the more information SolidWorks needs to figure out. You can see that there are so many triangles that the part appears to be red from all the lines. Now, you may think that this is great because we have a lot of tiny triangles that very specifically construct our part geometry, but this is actually not good. This is a lot of information, and it took a long time to mesh. Think about how long it could take to run a whole simulation on this part. So that's not going to help us either. What I'm going to do is I'm going to set this to 0.7, and I'm going to hit mesh just to see what it looks like. And under gradation, I'm going to keep the gradation between smooth and sharp. I'm going to just set it right in the middle. We're going to see what that's going to do. So when I hit mesh, it took about 2 seconds to process, and you can see that I get a pretty accurate picture of my part. But there are some little issues here. One thing that you notice is that my fillet is very faceted. It's made up of maybe 3 or 4 lines only. Now that's not very accurate. You can also see that the fillet that was on this boss is abbreviated. It looks more like a chamfer than it does a fillet. So to fix these little issues, we're going to come over here to local refinement and we're going to click on auto. Now we get a couple more options. The mesh tolerance is basically how much smaller the triangles can get based on the original triangle size that we use. It's a ratio. So if I made this, the same size as the triangle size, then it's not going to help us. This needs to be a proportional size. So let's see what happens when we set this to 1. We're going to mesh and we're going to see that that hasn't really changed anything. Now this number needs to be much smaller. So if we have 0.7 as our triangle size, let's try 0.1 for our mesh tolerance here. And we're going to let SolidWorks do an auto local refinement. So as you can see, this representation, though there are a lot of triangles, and though I may need to make my triangle size larger, this is a much better representation than what we had before. One thing you'll notice is that the really dense areas are in the fillets. See right here, very red, the fillet here, very red, and this fillet right here is also very red. The reason for that is because we chose local refinement, and so SolidWorks is smart enough to understand where some of our more curvy and organic sections of our part are, the parts that need a little bit more refinement in terms of our geometry. So we're going to up this number a little bit more. I'm going to make this 1 for triangle size, and I'm going to make the mesh tolerance 0.2. And when we hit mesh, we're going to get a nice in-between value. A great way to tell if your mesh is too meticulous is if you hit mesh and it takes a long time for it to process. Say 7 seconds, 8 seconds. You may not want to go that heavy depending on your computer system. So you want to kind of watch out for that. This takes maybe 3 or 4 seconds to do it, and we're going to leave it at that for this example. So I'm going to come up here and hit next. And SolidWorks gives us a couple parameters here that we can look at just for reference. Waterproof means that the mesh is completely closed. That's very important. The number of mesh groups is 1, obviously because we only have one part. Very bad elements can be any sort of issue with the mesh itself, maybe a flipped hexahedral element or something like that can be a bad element, and it can be something that is pernicious when it comes to processing. And so we're just going to hit OK to the summary. And this is going to bring up a new window. And under here, you're going to see mesh analysis, edit, node, and save current mesh. So the things that I want to call your attention to in this window is one, mesh topology. So if you double click on mesh topology, you're going to see a list of different topology characteristics. And so here you see non-manifold elements. If you see a number here, it means that there's a non-manifold element. If you see intersection element, that there's a number here, it means that there are intersection elements. It means that elements are within each other, which is not what you want to have. Element intersections between bodies, if you have more than one body and the elements or the hexahedral elements that I was talking about before, if those are intersecting, then you're going to see a number here as well. So within our single part, we see that we don't have any of these issues. So I'm going to hit OK. And some other things that you may want to look at are the mesh quality. So I can double click on mesh quality. And this is going to give us a couple other sort of points of information. Bad elements comes up here, 0.00%. So we know that our mesh is good. Worst elements also 0.00%. And good elements here says 100%. So our mesh quality is just fine. And here you're going to see some options for editing your mesh. So if you have some issues here with your mesh topology and mesh quality, you may find that you may need to use this edit sort of list here to fix your mesh. You may need to fill a hole or delete a triangle. So if I double click on delete triangle, you're going to see that I can come over here and I can select some triangles, and if I wanted to delete them, I could just hit apply and that would get rid of them. So we don't want to do that because our mesh is totally fine. You may also want to fill a hole. If you have a hole, it'll allow you to fill a hole, but since we don't have any holes, when I double click on this, it's going to say this mesh has no hole, and that's a good thing. And here you can also merge and adjust nodes. Those are the points on the edges of your hexahedral elements. And now that we see that our mesh is fine, we can just continue here in our wizard. So I'm going to hit next. And we want a tetrahedral mesh. So we're going to stay with this option. We're going to continue. And what's going to come up here is we're going to be finishing off our options for the mesh. And under here, under parameters, there's tetrahedral and there's hybrid. And if I click on hybrid and I hit transform, you're going to see it takes a bit of time to load. And you're going to see that part of my model is missing. And so you may be wondering why. Well, over here under profile, it's actually cut away a piece of my model based on the X, Y, and Z axes. So if I add to this, you're going to see that my part comes back. And the less of this that I have in this direction, this X profile here, the less of the part I'm going to have. So why is this useful? I mean, why is SolidWorks trying to get rid of part of my mesh, which, as we saw before, was 100% waterproof? Well, the reason is because, like I mentioned before, analysis is very taxing on the system. And so you don't want to run an analysis on a section of your model unless you really need to, because it's going to take time to run that analysis and it's going to tax your system. So when I add or subtract from this, I can kind of change the amount of simulation time that I need. So what we're going to do is I'm just going to show what these can do, and then we're going to dial this up all the way to 100. So we're going to have our entire part as part of the analysis. So see, if I bring this all the way to here, you're going to see that this is completely filled in. Now, what happens if I move this slider? Well, that's going to get rid of that section of the model. Now, what if I move this slider? Okay, that's going to get rid of that part of it in this direction. Oh, now what if I move this one? Okay, now it's going to remove it in the other direction. Or the Z, that removes it from the bottom. And if I click on negative Z, what do you think is going to happen? It removes it from the top. So these are really just ways of cutting away a section of your mesh in order to have less tetrahedral elements in total to do the analysis with. So we're going to leave it at this for our profile. We want to select the entire model, and we're going to continue. And as you can see, here's our model and here's our mesh. And everything is fine to date. We can actually, from this window as well, delete part of our model if that's what we want to do. But for this example, we're just going to come up here and hit OK. And after that loads, and it may take some time based on how many tetrahedral elements you're using, you're going to come back to, I'm sorry, hexahedral elements you're using. It's going to bring you back to our main screen. Now before, you may remember that we had mesh, input, and results as the three things that were shown here. We now have a lot more options to choose from. The next thing that we want to go to, because of the fact that we're done with the mesh tab, is we want to click on this little minus sign, and that's going to close up our mesh window here. So that way we don't really need to think about it because we're pretty much done with that tab. And what I'm going to do from this point is I'm going to click on Polymer. That's the next thing that we want to choose. So it's going to bring you to this window. Now you may be wondering, what does this all mean? Well, the first thing you'll notice is it gives you a viscosity over shear rate graph. That can be very helpful. So I can double click and that's going to remove some of these points. And the points that it's giving you are based off of temperature in Celsius here. So again, I can double click with the left mouse key and that's going to remove them or show them. The other thing to take note of here is the 4,000 materials within the plastic database, or actually over 4,000 materials within the database. And so you can sort these materials by family, which I'm doing the way I have it set right now, or you can sort by company. So instead of sorting it ABS, ASA, BMC, EPDM, all these materials, I can click on sort by company, and all of a sudden the brand names of the companies that make the materials is going to come up instead. And so if I don't want to look through this whole list, I can just come over here and click on Find. And I can type in the material I want, or the company. Basically any keyword that's going to help me find the material I want. So I typed in Bayer here. So I'm going to close this. And from here, I want to call your attention to a tab all the way at the top right, which seems a little bit out of the way, but it's a very important tab for information about Polymer. So I'm going to click on Polymer Material Parameters, and you're going to see that a bunch of information comes up based on the material that I choose. So if I click on this LDPE by Basel, you're going to get melt temperatures, the mold temperature, you'll get ejection temperature, and all the sorts of numbers and measures that you're going to need within your analysis. So we're going to hit OK. And before we do that, I'm just going to select a different material. I'm going to click on ABS, and I'm just going to select the first thing that comes up, this ABS from A. Schulman, and I'm going to hit OK. So what I did just now is I set the material for my part. And you're going to see in the top right that it comes up. And this is very helpful because you want to make sure that you're using the right material in your analysis. And so it's very helpful that it comes up in the top right and you don't choose the wrong material by accident and then you run a whole analysis and you send it to the vendor and maybe it comes out wrong for that reason. Other things you're going to see are the amount of elements here. And so the higher this number, obviously the longer it's going to take to process. The other thing, of course, is that it says solid here, and the reason is because this is a solid analysis, and so it makes sense. We didn't do a shell analysis for the mesh, we did a solid mesh. And so from here, what we can do is we can go to our fill settings next. I'm going to come up here and click on the minus sign to close the material input, because we don't really need that anymore. So I'm going to come down to fill settings, double click on fill settings, and you're going to see a bunch of parameters that come up for things like melt temperature, mold temperature, injection pressure, and etc. And these really come from our material. So the material is dictating the mold temperature. Now that usually sounds like something that is based on the machine, but this is the mold temperature that's specified and sort of a recommendation from the manufacturer in terms of that spec sheet. So there are a lot of other options here. We're not going to go through every single little thing right now for this example, but there's definitely a lot of power in terms of the settings that you're going to use with your material. For instance, I can uncheck auto, and you're going to see that I could set the filling time that I want for my part. So I'm going to close this. And with those settings filled in the way they are, I can now go to injection location. You can find injection location under the boundary conditions right here. And so you can double click on injection location, and that's going to bring you to a new feature manager here. And the first thing that I want to do is I want to create an automatic injection location. So I'm going to come down here to this button called Add Injection Locations Automatically. And if I click on it, I can select how many I want. I only want one of them. You're going to see that once I select that number, SolidWorks comes up with a location automatically that it chooses based on its algorithm for the injection location. So let's say that we don't want this location. We'd rather choose our own. We can come down here and we can either choose delete injection location or delete all injection locations. So I'm going to click on delete injection location, and you can see that the injection location is now not in our menu over here. So we want to add our own. The way we're going to do that is by clicking over here on this first button called Add Injection Location. So you can click on it, and you can now select an edge, and you're going to see that my injection location pops up accordingly. So we can change a couple different things here if we'd like. I can change a pointer diameter to be larger, and that's pretty much recommended because the pointer size is going to make it easier to view. It's going to be easier to look at if you need to show this to a higher up or a colleague. Now that we have that selected, we can come up here and check OK. We now have our injection location selected. So at this point, I'm going to click on this minus sign to bring up the boundary condition since we're not using it anymore. And I'm also going to bring up the fill settings, which we've already done, and the material. And at this point, we can run our flow simulation. So I'm going to double click on flow, and you're going to see that an analysis manager comes up. And if you maximize this, you can see some information about the ongoing simulation. You pretty much have to wait until this wizard closes. And when it finishes, you'll have your whole simulation finished. So what it's doing right now is it's actually calculating every second by second, exactly the way that the flow is going to work. And there are a couple different options under run. We chose flow, but you can also choose flow and pack, as well as flow, pack, and warp. And the flow, it only shows you the way that the plastic is moving through the mold. But the flow and pack shows you the packing as well, the way that it actually stays in the mold. And the warp shows you the way that the plastic part actually bends once it cools. So you can see that our analysis is coming to fruition here. We're getting a couple new windows that are coming up. So we have under here results under our feature manager, and you can see that there's a bunch of different results that come up based on our mesh, based off the material parameters, based off all the sorts of inputs that we gave. So our simulation is finished and our results are shown. On the right side of the screen, you can see under the results advisor that SolidWorks has a red, yellow, and green traffic light here, and the colors all mean different things. So we have a green light, which is good. What that means is that the specified limit of our injection molder is way higher. In this case, the 5,213 psi that we have is 66% less than the maximum injection pressure that the machine has. So generally speaking, you want to make sure that the amount of psi of material coming into the mold is a certain factor of safety less than the machine's capability. And the reason for this is you don't want to push the machine's limits. And so if you see a yellow light come up here, then you're within a range that's kind of in the middle. And if the red light comes up, it likely means that you're pushing the limits of the machine. The amount of PSI you have is approaching or above the maximum PSI limit that the machine has based on our inputs. So that being said, there's some information about fill time, which is the first flow result that comes up. And the main thing that we want to remember with our fill time is we want to make sure that our fill is even. So us having the injection location here on this side or on this side right here in the middle is going to be a pretty even fill. And I can come over here to the bottom left and hit play, and you can actually see the material entering. And the main thing to notice for starters is that the color red at the end, which is the 1.429 seconds into the shot, is at the outskirts of the part. And that's a good thing. You don't want to have a part where only a certain section of it is filled in and the rest of it is not filled in at all, or all very red, because what that means is that the mold is not filling equally. Now, in a perfect world, every little inch, every little crevice of your part would be filled all at once. But in the real world, we can't do that. We have one injection location for this part. We would have, I would suppose, an edge gate here at this edge. The material runs in, and from our simulation, we could see that the shot is pretty even across the whole part. So I'd like to call your attention here to the left side. If I click on weld lines, you're going to see the weld line propagation that comes up based on the injection location. And so, as we likely know by now, weld lines are unavoidable. It's just a question of where they're going to be. So here you can see that there are a couple weld lines along the ribs here. And this is a weak spot. This is where two cold fronts touch. And the angle at which they touch determines how bad that weld line is going to be. So it's something that is for looks. You'll see this come up on your part and it won't look pretty. And it also is a weak spot, as I mentioned. So there are some weld lines here based on the injection location. and there's some weld line here as well. And so I can run the analysis again to show you what that looks like. And I can change the speed, so I can dial this down here and run the simulation. And you can see these two cold fronts, they're about to touch right here in this spot. And if I go back to weld lines, or let me play that one more time just to really bring it home. So these are two cold fronts here, and they touch right here at this point. You can see them touch. And the same thing goes for over here on this boss. There's a weld line across here. And there's a weld line along the edge right here where the ribs are. So if I go back to weld lines, you're going to see that those locations are specified based on these lines. And the injection location, if we change it, is going to change where those weld lines propagate. So I'm going to turn this off. And we're going to look at air traps as well. So air traps are something that you want to try to dial down on. You want to make sure that you don't have weld lines. Air traps that are going to create gas marks, because that's what they do. Basically, an air trap is when you have a few fronts of material creating a ring, and as that ring gets smaller and smaller, the air inside is eventually going to combust and create a gas mark. So you can see that there's going to be a gas mark here because there's a bubble of air that gets infinitesimally small until it just explodes inside the mold. And you can see that there's one here at the end as well, and one inside the rib. And again, that's anywhere where a bubble is formed within the material propagation. So I'm going to stop this, and we're going to look at a couple more parameters. Now you can see that there are a lot of results here, but we kind of want to weed out what we don't need so that we could look at what's really necessary to understand. So I can click on pressure at end of fill, and this is really important because I could see in megapascals how much pressure there is at certain sections. So you can see right here that the pressure is very low, and that can be a problem. I may need to move my gate a little bit over, so that way this blue section turns a little bit more yellow and green so that everything is a little bit more even. Generally speaking, you want to go for evenness within the pressure, because if you don't have enough pressure at a certain section, you may get a short shot. The material may not be able to flow very easily, and so you're going to have half a part come out of your mold. Let's look at one or two more things here. We can come to sink marks, and this is probably one of the most useful underneath maybe pressure at end of fill, because it's going to show you all the places where you're going to experience shrinkage. So as you can expect, sections with a little bit more material are going to obviously have more sink marks, because the more material you have in a section, the more it's going to shrink. So here we have a boss, and the edge here has a good amount of material, which is going to shrink a little bit. And if you look on the other side, you can see that on the inside here, there might be a shrink mark as well. And the way that SolidWorks decides to show it is in millimeters. So you could see 0.07 millimeters. So 0.07 millimeters, likely not very noticeable, but there will be times where you're designing a part and you may not realize that there's a large bulk of material in a certain area. And so you may need to change your gating, or you may decide to core out that section in order to not experience sink marks. So those are our results, and those are the sorts of things that we can learn from SolidWorks analysis.